All dimensions in physics explained simply. Welcome to a journey through the hidden layers of reality. When we hear the word dimension, we often think of length, width, height, or maybe even science fiction portals. But in physics, dimensions are far richer, stranger, and more fundamental. Over the next 5 hours, we will travel across the familiar dimensions of space and time, higher dimensions predicted by theories like string theory, quantum dimensions, fractal dimensions, emergent dimensions, and the biggest question, how many dimensions does reality truly have? By the end, you'll understand dimensions more clearly than most physics students. What is a dimension? Introduction. A dimension, in the simplest mathematical and physical sense, answers a very fundamental question. In how many independent directions can something move or change? This idea may sound simple, but it forms the entire backbone of how the universe is structured. To visualize this, imagine an insect crawling along a straight piece of string. The insect has only one possible direction of movement, forward or backward along that line. It cannot move sideways or up. Its entire world is restricted to that single pathway. This is what we call one-dimensional space, or 1D, where every position can be described using just one number, like an address on a ruler. Now, expand this world slightly. Picture an ant moving freely across the surface of a sheet of paper. Suddenly, the ant is no longer limited to a single line. It can walk forward, backward, left, or right. It can trace circles, squares, curves. Its movement requires two coordinates to describe any point. For example, an X position and a Y position. This is two-dimensional space, or 2D, a flat world where creatures can move in two independent directions. This is the same dimensional world used for maps, drawings, floor plans, and screens. Finally, imagine the space we humans live in. Unlike the ant, we can walk not just forward-backward and left-right, but also up and down. This third independent direction introduces three-dimensional space, or 3D. Here, any location around us can be described using three coordinates: length, width, and height, or X, Y, and Z. These three dimensions give objects volume, allow buildings to rise into the sky, and let birds fly above us. The everyday universe, the physical space we can see, touch, and move through, is fundamentally three-dimensional. But physics teaches us something much deeper. Dimensions are not merely measurements of distance. They are the fundamental rules that determine how things can move, interact, or even exist. A dimension is like a degree of freedom, a direction in which change is possible. If a dimension did not exist, movement or variation in that direction simply could not happen. For example, without height, stairs would be meaningless. Without time, motion would freeze. Without abstract dimensions, many modern physics theories would collapse. So when physicists talk about dimensions, they're not just describing shapes or geometry. They are describing the deep structural framework that determines how reality behaves. Higher dimensions, extra dimensions, quantum dimensions, and even time itself are all part of this expanding idea.
When we begin our journey into the world of dimensions, the very first and most fundamental concept we encounter is the zero-dimensional point, often called simply a point. A point is the absolute simplest entity we can imagine in both physics and mathematics, but its simplicity is deceptive because it forms the foundation for everything else that comes after. In zero dimensions, there is no length, no width, no height, no thickness, and no possibility of movement within the dimension itself. A point does not stretch, it does not extend, and it cannot contain anything. It is pure position. Nothing more, nothing less. When we draw a dot on paper, we are not actually drawing a point. We are drawing a small 2D circle that represents a point. The true mathematical point contains no physical area at all. It is an idea, an abstract coordinate, a location in space with absolutely no size. Zero-dimensional space is a space consisting of only one possible location. If you imagine living inside a 0D world, your entire universe would be a single fixed spot. You could not turn left or right, you could not step forward or backward, and you could not jump up or down. You wouldn't even understand the idea of movement, because motion requires at least one dimension to move through. In a 0D existence, the concept of distance becomes meaningless. There is no space to measure, no direction to choose, no path to follow. It is a universe of perfect stillness, not because things don't move, but because movement itself has not yet been invented. Despite being so simple, the zero-dimensional point is incredibly important because it is the building block of all higher dimensions. In geometry, this is expressed through the idea of extension. If you take a point and extend it in one direction, meaning you imagine many copies of that point arranged in a straight path, you get a line, which represents the first dimension, 1D. If you then take that line and extend it in a new direction that is independent of the first, the line sweeps out a plane, giving us the second dimension, 2D. If you then lift that plane upward in a direction neither parallel nor contained within it, you generate a volume, which becomes the third dimension, 3D. This step-by-step growth shows that every new dimension is created by extending the previous one. And at the very base of this pyramid lies the tiny, overlooked, but absolutely essential 0D point. From a mathematical perspective, a point is described by a set of coordinates. In 0D, that set has no size. It is just a single fixed coordinate, like 0, or A, or any label. But as soon as we move to 1D, points gain one coordinate, like X. In 2D, they gain 2, xy. In 3D, 3, x, y, z, and so on. Therefore, 0D can be understood as the origin of all coordinate systems. In physics, points appear everywhere. The location of a particle, the center of a black hole, the singularity at the Big Bang, or even in quantum mechanics, where abstract points represent states in a space of possibilities. Every model of reality begins with defining points, because without them, space itself cannot be described. Philosophically, the zero-dimensional point represents the idea of pure existence without form, structure, or extension. Many thinkers compare it to a foundational concept, something from which more complex realities emerge. In ancient mathematics, the point was viewed as the seed of geometry. In modern physics, the singularity of the Big Bang, the moment when the entire universe was compressed into no space at all, is often described using 0D language. It is not literally a point in space. Rather, it is the absence of space from which space itself expanded. This parallel shows how the idea of 0D appears even at the deepest level of cosmology. The importance of understanding 0D cannot be overstated. If you fully understand what a point is, you can understand how dimensions grow, how geometry is built, how space is structured, and why movement requires dimensionality. Zero dimensions are the silent beginning of the universe's geometric story. Before there could be lines, there had to be points. Before there could be surfaces, there had to be lines. Before there could be volumes, there had to be surfaces. And before there could be space as we know it, there had to be the simplest concept imaginable, a point. This is why we always start our exploration of dimensions with the zero-dimensional point. It is the conceptual spark from which all higher dimensional structures arise. Every shape, Every object, every physical universe is formed by extending, arranging, and transforming points. The point is the origin. It is the foundation. It is the beginning of dimensions themselves.
First dimension: lines and length. To understand the first dimension, we must imagine a world stripped of all complexity. No width, no height, no surface, and no volume. The first dimension, or 1D, represents the idea of a universe made of nothing but a single straight line, an infinitely thin pathway along which any object can exist or move. In this space, the only meaningful action is movement forward or backward, because those are the only two directions the dimension allows. There is no possibility of turning left or right, nor rising upward or sinking downward, because those directions simply do not exist in a one-dimensional reality. If you were a creature living in 1D, you would have no concept of sideways or above. Your entire world would be a seamless, unending line stretching before and behind you. In this world, the position of anything can be described using only one number, which we call a coordinate. This single value, often labeled x, represents your location on the line, much like the markings on a ruler. For example, x equals 5 might tell us that an object is 5 units to the right of the starting point, while x equals -3 might indicate it is 3 units to the left. Because only one number is needed, 1D is the simplest, most fundamental type of space that still allows the idea of distance and direction to make sense. This single direction freedom is known in physics as a degree of freedom, and in 1D there is exactly one such degree. To visualize this abstract concept, consider beads sliding on a wire. Each bead can move along the wire, but it cannot escape or deviate from the path. Its entire universe consists of the line defined by the wire. If other beads exist, they must share the same line, lined up like pearls in a necklace. There's no way for one bead to pass another without breaking the wire, because there is no room for one bead to go around. This gives us insight into how restricted a 1D world would be. Objects cannot bypass each other or interact in complex ways because the dimension is too simple to allow it. A real-world analogy with more structure is train tracks. A train is forced to follow the exact path laid by the rails. It can't spontaneously turn left into the field or rise into the air. Although the world around the train is 3D, its movement is effectively confined to a 1D path. This is why physicists sometimes model complex systems using 1D approximations, because many forms of movement or flow behave as if they are restricted to a single pathway. Think of traffic on a single-lane road, electrons moving through a narrow quantum wire, or sound waves traveling down a slinky. All of these systems behave like 1D motion, even if they exist in a more complex environment. Surprisingly, the concept of the first dimension appears even in the structure of life itself. A DNA strand, although physically three-dimensional, behaves mathematically like a one-dimensional sequence of coded information. Each base, A, T, C, or G, exists at a specific position along the length of the molecule. Enzymes that replicate or read DNA move only along its length, never sideways into imaginary directions that don't exist. This makes DNA a perfect real-world example of how nature uses one-dimensional structures to store massive amounts of information in a simple, linear format. The order of bases forms a 1D pattern that ultimately shapes every living organism. In physics, the first dimension also provides a foundation for understanding motion. When you drop a ball, its movement can be analyzed in one dimension, just up and down, even though it exists in 3D space. Many physical equations begin by considering simplified 1D models because they reveal the core behavior of a system without the complications of higher dimensions. Waves on a string, heat traveling along a rod, particles confined in narrow channels, these are fundamentally one-dimensional phenomena. For example, a wave in 1D moves only left or right, making it easier to study the nature of oscillations, interference, and energy transfer without dealing with complex patterns in 2D or 3D. Mathematically, the structure of 1D is incredibly clean and foundational. 1D coordinate system has only one axis, the x-axis. Distances between points are simply the difference between their x values, and there is no concept of angles or rotation because those ideas require at least 2 dimensions. A shape in 1D can only be a line segment defined by 2 endpoints. There is no such thing as a square, a circle, or a cube because these shapes require additional dimensions to even exist. A living creature in 1D would have no concept of sideways or above. It would be nothing more than a point or a segment floating on an infinite line. Most importantly, the first dimension is the gateway to all higher dimensions. A line is formed by extending a point, 0D, in one direction. A plane, 2D, is formed by extending a line in a new direction. A volume, 3D, arises from extending a plane into yet another direction. Without the first dimension, there would be no second, no third, and no concept of physical space at all. The idea of 1D gives us our very first taste of what it means to move, to measure distance, to define direction, and to conceptualize pathways in the universe. Thus, the first dimension is simple but profound. It forms the basis of geometry, physics, biology, motion, and information. It invites us into the world of dimensional thinking, showing how even a single line can contain deep scientific meaning. By mastering the structure and behavior of 1D space, we prepare ourselves to understand the richness and complexity of the dimensions that follow.
When we move from the first dimension to the second, we introduce something revolutionary, a brand new direction. In 1D, a creature can move only forward or backward along a straight line. But the instant we add a single new direction, one that is completely independent of the first, we create an entirely new type of world, 2-dimensional space, often called 2D. This new direction is what we commonly think of as sideways, but in this context, it represents an entirely separate axis of movement. In 2D, a creature can now move forward, backward, and left-right. These 2 independent directions allow beings in such a world to navigate a flat plane, like walking across the surface of a sheet of paper. This change may sound simple, but mathematically and conceptually, it is enormous. Adding a new dimension introduces new freedoms, new shapes, and new ways of interacting with space. To help us truly understand this shift, imagine living in a world called Flatland, a famous fictional universe from the classic 1884 book, Flatland, A Romance of Many Dimensions by Edwin Abbott. In this story, Abbott describes a 2D universe inhabited by sentient geometric shapes, lines, triangles, squares, and circles, who live entirely on a flat surface. They have no concept of height because up does not exist for them. Their entire reality is constrained to a plane, like ink stains sliding around on a sheet of paper. A flatlander cannot jump, cannot stack objects, and cannot see a sphere or cube the way we do. Instead, everything in Flatland appears as lines or segments, because a 2D creature perceives only slices of objects, not full volumes. If you placed your hand into flatland, the inhabitants wouldn't see your hand as a whole. They would see a series of line segments that change shape as your hand passes through their world. This book is not just a story, it is a powerful mental tool that helps us understand what limitations a lower dimensional being would experience and how difficult it would be for them to imagine higher dimensions. Flatland also reveals a deeper truth. Moving from one dimension to the next completely transforms the nature of existence. For a 2D creature, the idea of a third dimension, height, is impossible to visualize or logically comprehend, just as humans struggle to understand the fourth or fifth dimensions. A flatlander cannot imagine up, just as we struggle to imagine movement outside our 3D space. If a 3D being, like a human, visited Flatland, we would seem godlike. We could look into their houses without opening doors, because we exist outside their plane. We could lift a Flatlander off their surface, something they would interpret as vanishing from reality. And we could interact with their world in ways that seem magical simply because we exist in a higher dimension. Likewise, higher dimensional beings, if they exist, would appear magical to us, not because they break laws of physics, but because they operate in spatial directions we cannot imagine. The concept of flatland isn't just science fiction, it is a profound tool for understanding how dimensions stack and how beings in higher dimensions might interact with the lower ones. Just as a flatlander can't understand 3D, humans find it difficult to conceptualize 4D or 5D space. But by studying how flatlanders perceive their world and how a 3D being appears to them, we gain insight into how we might appear to a 4D being. They could see inside our bodies without cutting us open, access locations that are separated in 3D with a single higher dimensional step, and move objects in ways that defy our expectations. Flatland essentially serves as a bridge between simple dimensions and the mind-bending possibilities of higher dimensional physics. Thus, the second dimension is not just a flat surface, it is the gateway into understanding how dimensions expand, how each new directional freedom radically alters reality, and how beings in higher dimensions might interact with the lower ones. Adding one new direction does not merely stretch space, it creates an entirely new realm with its own rules, its own limitations, and its own mysteries.
When we enter the third dimension, we step into the reality we are most familiar with, the world of length, width, and height. These three independent directions give shape to everything we see, touch, and experience. In 3D, space is no longer a flat plane like in 2D. Instead, it expands outward in every direction, creating a vast environment filled with depth and volume. Every object around us, from mountains to molecules, occupies three-dimensional space. To describe any location in this world, we use a coordinate system made of three numbers, x, y, and z. Each coordinate captures a direction: left, right, forward, backward, and up, down. Together, they act like a universal address for every point in space, allowing us to map cities, animate movies, simulate physics, and even model the universe itself. The jump from 2D to 3D is profound because it allows objects to have volume, not just shape. In 2D, you can draw a square or a circle, but these shapes have no thickness, they're flat. In 3D, those shapes expand into cubes and spheres with measurable mass and structure. Volume is what allows us to pick things up, stack objects, and move around one another. A creature in 3D can walk around obstacles, climb over things, or even go underground, possibilities that 2D beings can't even imagine because they lack the essential freedom of height. Our bodies, the environment, buildings, clouds, planets, everything takes form because the third dimension exists. Without height, your body would collapse into a flat shape, your organs wouldn't function, and the world would lose its complexity. Furthermore, the third dimension is where gravity truly reveals its importance. Gravity, in our everyday understanding, is the force that pulls us downward.
But in physics, especially in Einstein's theory of relativity, gravity actually shapes space itself, bending the fabric of the three-dimensional world. In this view, massive objects like Earth or the Sun warp the geometry of 3D space, and this curvature guides how objects move. Planets follow curved paths around the Sun not because they are pulled by a mysterious force, but because the Sun's mass bends the space around it. This is only possible in a 3D environment, and more accurately in 4D spacetime, where the structure of space can be distorted. Even the way rivers flow, the way galaxies spin, and the way you stand on Earth are tied to the three-dimensional nature of space and how gravity acts within it. Another property unique to 3D is how light spreads out. In one dimension, light could only travel forward or backward. In 2 dimensions, light would expand in a flat circle. But in our 3D universe, light radiates outward in all directions, forming expanding spheres of illumination. This behavior affects everything from how we see objects to the structure of the cosmos. For example, the brightness of a star decreases with distance because its light spreads across a larger and larger spherical surface. This principle governs the design of flashlights, laser beams, telescopes, and even the intensity of Wi-Fi signals. Light's ability to travel freely in 3 dimensions also allows shadows, reflections, transparency, and depth perception to exist, visual phenomena that would look completely different in a lower dimensional world. Perhaps the most important truth about the 3rd dimension is that our physical universe as we experience it exists here. Everything from solid objects to liquids and gases behaves according to the rules of 3D geometry. Our sense of direction, our ability to navigate, and even the structure of our brains evolved within this 3-dimensional environment. The chemistry of life depends on 3D molecular shapes. Proteins fold into intricate 3D forms, DNA twists into a helical structure, and cells build 3-dimensional tissues. Life itself is only possible because molecules can form complex spatial arrangements that cannot exist in 1D or 2D. Yet despite how natural and complete the 3rd dimension feels to us, physics suggests that 3D is not the ultimate structure of reality. The world may appear 3-dimensional, but many modern theories propose that there are hidden dimensions beyond the ones we experience. Some theories argue that space may be a projection of deeper dimensional processes, like a hologram. Others propose that tiny, curled-up spatial dimensions exist at scales far smaller than atoms. Even time is often treated as the 4th dimension, merging with 3D space to form spacetime, a unified fabric that shapes the behavior of every particle and planet. Quantum physics, string theory, and cosmology all hint that the universe is more mysterious than our senses reveal. So while the 3rd dimension is our everyday reality, rich with volume, shaped by gravity, illuminated by light, and filled with life, it is also just a chapter in a much larger story. Beyond the familiar walls of 3D space lies a vast, unexplored landscape of higher dimensions, waiting to be understood.
When Albert Einstein introduced the concept of spacetime, he did not simply add a new idea to physics, he fundamentally changed the way humanity understands the universe. Before Einstein, scientists believed space and time were 2 separate things. Space was the 3-dimensional stage where matter existed, and time was a completely independent flow that ticked the same for everyone, everywhere. But Einstein shattered this worldview by showing that space and time are not separate entities at all. They are woven together into a single 4-dimensional fabric called spacetime. This fusion is not metaphorical, it is a literal, mathematical, and physical merging. The universe does not have space and time. It has spacetime, one unified structure. To understand why Einstein regarded time as a dimension, we must think about what a dimension truly means. A dimension is an independent direction in which something can move or change. In space, we can move left or right, forward or backward, up or down, 3 separate freedoms. But every event in the universe also requires a when in addition to a where. This when is not optional,
It is essential. You cannot specify the location of anything, an explosion, a heartbeat, a collision, or even a conversation without stating when it happened. This means time is not just a clock on the wall, it is a coordinate, just like X, Y, and Z. Every event in the universe has 4 coordinates, its 3 spatial positions and 1 time position. This is why Einstein said time is the 4th dimension. Einstein also showed that movement through space is inseparable from movement through time. Even when you are sitting still, your body is constantly traveling forward in time at 1 second per second. Motion changes how time flows, and time changes how motion appears. When you walk, drive, or even stand up, you change your speed through space. And because the speed of light is fixed, your speed through time adjusts to compensate. According to relativity, the faster you move through space, the slower you move through time. This is not science fiction. It has been measured using airplanes, satellites, and extremely precise atomic clocks. Astronauts on the International Space Station age very slightly slower than people on Earth. This intimate link between space and time proves that they are not independent, they are the 2 faces of the same underlying reality. Perhaps the most profound implication of space-time is that gravity is not a force pulling objects downward, it is the curvature of space-time itself. When Einstein studied gravity, he discovered that massive objects like planets, stars, and black holes bend and distort the fabric of space-time around them. This curvature tells objects how to move. A planet orbiting a star is not being pulled by an invisible force, it is simply following the straightest possible path through a curved 4-dimensional geometry. Even light, which has no mass, bends when it passes near massive objects because it too must travel through the curved structure of space-time. This bending has been observed many times, including during solar eclipses when starlight curves around the sun exactly as Einstein predicted. The idea that gravity affects time is one of the most astonishing predictions of Einstein's theory. If mass curves space-time, it affects both space and time. The closer you are to a massive object, the slower time passes. This means clocks tick differently depending on altitude or gravity strength. Time on the surface of the Earth flows slightly slower than time in orbit. GPS satellites must account for this difference, otherwise their navigation systems would drift off by miles every day. So when we say gravity bends time, we mean it literally. Your heartbeat, your aging, and every moment you experience are subtly influenced by the curvature of space-time around you. All of this leads to one of the most beautiful ideas in relativity. Your entire life is a path through space-time called a world line. Your world line is the 4-dimensional trail formed by your existence from the moment you are born to the moment your life ends. Every second that passes extends your world line forward in time, just as moving through space extends your path across the Earth. For an object that never moves, say a rock on the ground, its world line is perfectly straight and vertical in the time direction. For a traveling person, their world line curves and bends as they move through different places and times. In this representation, your whole life can be visualized as one continuous, unbroken line stretching through the universe's 4-dimensional fabric. This is not a poetic idea, this is how relativity literally models the universe. Thus, the 4th dimension is far more than a mathematical idea. It is a fundamental part of reality itself. Time shapes existence just as deeply as the spatial dimensions do. Space-time determines how planets orbit, how light travels, how GPS works, how clocks tick, and how we age. Einstein revealed that our universe is not a floating stage where objects move independently. It is a dynamic, interconnected 4D structure where time and space are inseparably intertwined. And yet,
As profound as this discovery is, physics suggests that even space-time is not the end of the story.
When we step beyond the familiar 4 dimensions of space-time, we enter a realm that is far more abstract and conceptual, the 5th dimension. In many modern interpretations of physics, especially in certain versions of string theory and in speculative cosmology, the 5th dimension is used to describe a new kind of structure in the universe, the space of different possible timelines. Unlike the first 4 dimensions, which describe the physical position and time of events, the 5th dimension is often imagined as a dimension of possibility, a place where every choice, every chance event, and every possible outcome branches into its own version of reality. To understand this, imagine that your entire life is a path through space-time, a world line in 4D. At every moment, you make decisions. You take a job, choose a partner, cross a street, answer a phone call, walk into a room. Each decision leads you down one specific path. But what about the paths you didn't take? What about the moments when you could have turned left instead of right, said yes instead of no, or missed an opportunity instead of grabbing it? These alternative possibilities, though never realized in your personal world line, still exist as logical paths that could have unfolded. In the idea of the 5th dimension, all those unrealized paths are still part of reality. They simply lie along different branches of the 5D structure. Thus, the 5th dimension captures not just what happened, but everything that could have happened. Every decision point becomes a branching moment, splitting reality into multiple possible timelines. One timeline leads you to becoming a doctor. Another leads you to becoming a traveler. Another leads you to meeting different people, facing different challenges, or living in a different city. From this perspective, your life is not a single fixed story. It is one thread among countless parallel possibilities woven through the tapestry of the 5th dimension. This branching idea is not just philosophy or storytelling, there are strong scientific motivations behind it. In quantum mechanics, particles do not follow one definite path. Instead, they exist in superpositions of many possible states until they are observed. Each potential outcome is real in the mathematical description of the system. The famous many worlds interpretation of quantum mechanics suggests that each time a quantum event occurs, the universe effectively splits into different branches, each representing a different outcome. For example, if a particle could move left or right, the many worlds view says it does both, but in separate parallel branches of the universe. Applied on a larger scale, this implies that the entire universe constantly branches into different timelines based on every quantum event, no matter how small. The 5th dimension is a way to visualize and organize these branching possibilities. Instead of imagining universes splitting endlessly, we imagine them all lying side by side along an additional dimension, a dimension of alternate histories. In this sense, the 5th dimension is like an enormous cosmic library of every possible version of reality that could arise from the same starting point. The Big Bang sets the initial conditions, and from those conditions, countless timelines branch and unfold. Splitting occurs not only because of human decisions, but because of quantum randomness, environmental differences, microscopic fluctuations, and every unpredictable event that shapes reality. You can think of it this way. 4D tells you what actually happened in your specific universe. 5D tells you every way things could have happened from the same beginning. Some scientists compare the 5th dimension to an enormous field of possibilities, where each point corresponds to a full timeline, from the birth of the universe to its end. If 4D is a single thread, 5D is the entire bundle of threads, each one representing a different history. This makes the 5th dimension incredibly rich and incredibly large, far larger than the 4D world we inhabit. To visualize it, imagine yourself standing at a crossroads where many paths radiate outward. In 4D, you choose only one path, and that becomes your life. But in 5D, every path exists simultaneously. One version of you took the left path, another took the right, another turned around,
Another didn't exist because your parents never met. These possibilities do not erase your lived experiences, but exist alongside them, forming a web of alternate universes all connected through the fifth dimension. This idea also hints at something profound. If a higher dimensional being existed, one capable of perceiving the fifth dimension, it would see all possible versions of events, not just the single timeline we experience. Such a being could see every what if, every alternate outcome, like reading multiple versions of the same storybook. It could see the entire tree of branching realities, understanding paths of destiny and chance from a perspective beyond our own. So in many interpretations, the fifth dimension represents the landscape of possibilities, the dimension where alternate histories, different choices, and parallel outcomes all coexist. It expands our understanding of reality from a single timeline to a vast branching structure, revealing that the universe might be far more intricate and multidimensional than our everyday experience.
If the fifth dimension represents all the different timelines that our universe could take, every possible chain of events branching from the same beginning, then the sixth dimension takes an even bigger leap. The sixth dimension expands beyond the idea of alternate histories and asks a deeper question. What if the universe itself could have formed differently while still obeying the exact same laws of physics? The sixth dimension is often described as the collection of all possible universes that share the same fundamental rules, the same equations, and the same constants of nature, but differ in how those rules play out. In 5D, we explored timelines that branched from a single universe's starting conditions. In 6D, we go beyond just alternate timelines of our universe. Instead, we step into a landscape containing entirely different universes, cosmic structures that formed differently right from the very beginning, yet still operate under the same underlying physics. To understand this, imagine restarting the universe billions of times. Each time, the laws remain identical. Gravity is the same strength. Light travels at the same speed. Atoms behave the same way. Quantum mechanics follows the same equations. But even with the laws unchanged, the initial conditions, the tiny fluctuations present at the moment of the Big Bang, can differ. And when the smallest seeds of the early universe are different, they grow into vastly different cosmic outcomes. Different Earths, different histories. One of the easiest ways to imagine 6D is to picture Earth forming in different ways in different universes. In one version, Earth forms slightly closer to the Sun. In another, it forms earlier or later. Maybe Earth becomes a desert planet, a water world, or a frozen wasteland. The continents might never break apart. Dinosaurs might never go extinct. A small difference in asteroid impacts or volcanic eruptions could dramatically reshape the evolution of life. All these outcomes are possible without changing the laws of physics. They arise simply from different initial setups, different evolutionary pathways for humans and life. In another 6D universe, humans might have evolved differently or not have evolved at all. Perhaps intelligence arose in ocean-based life instead of land mammals. A different species became the dominant civilization. The human body evolved additional senses, physical traits, or abilities. Humanity emerged earlier or later in the cosmic timeline. Every biological and evolutionary pathway depends on a chain of events. In 6D, each different chain is a separate universe because every slight variation in environmental conditions can lead to completely different outcomes over millions of years. The laws of biology remain the same, but the story of life changes dramatically. Different arrangements of galaxies and stars. On a cosmic scale, 6D includes universes where the structure of the cosmos itself is different. Galaxies may form in different shapes or locations.
Some universes might have more stars, others might have fewer. Black holes might be more common in some versions or rare in others. Dark matter might clump differently, creating new galactic patterns. All of these variations happen without altering the laws of physics. Instead, they come from how early cosmic fluctuations, tiny quantum ripples in the newborn universe, expanded and grew into galaxies, clusters, and superclusters. The sixth dimension contains universes where these ripples began differently, creating unique cosmic landscapes. Same physics, infinite worlds. What makes the sixth dimension distinct from the fifth is the scope of possibility. 5D gives you alternate timelines of our universe, different outcomes of the same starting conditions. 6D gives you alternate universes that share the same laws but have different starting conditions entirely. In other words, 5D equals variations of one universe. 6D equals all universes made possible by the same physics. If you think of reality as a game, the fifth dimension is like replaying the same game with different choices. The sixth dimension is like playing new rounds of the game where the map, characters, and scenarios change, but the game rules stay the same. A simple analogy. Imagine drawing many different paintings but using the exact same art supplies, brushes, and colors. Each painting is different, but the rules of what you can create remain unchanged. The sixth dimension is like looking at the entire gallery of all those possible paintings. Why the sixth dimension matters in physics. The concept of 6D universes arises naturally in string theory, where extra dimensions shape the structure of particles; cosmology, where slight differences in initial conditions create whole new universes in the inflationary multiverse; quantum mechanics, which allows multiple possible histories to coexist; statistical physics, which describes how systems evolve from initial states. Scientists use the sixth dimension to understand why our universe looks the way it does and why certain cosmic events, the formation of planets, stars, and galaxies, happened the way they did. It helps us ask profound questions. Why does the universe look like this and not another way? How sensitive is reality to the smallest changes? Are we living in one special universe among many? The sixth dimension brings a new level of reality. While the fifth dimension shows us alternate paths, the sixth dimension shows us alternate worlds. Worlds where history unfolds differently, life evolves differently, civilizations rise or fall in different ways, and the universe itself takes on different shapes. Yet through it all, the laws of nature stay identical. Same physics, same equations, different outcomes. The sixth dimension is the space of all possible universes that could arise from the same rules, revealing a vast multiversal landscape far larger than the branching possibilities of the fifth dimension.
When we enter the seventh dimension, we step beyond anything familiar, beyond timelines, beyond alternate histories, and even beyond the idea of universes that share the same physics as ours. In the sixth dimension, we explored universes that differed in their initial conditions, different galaxies, different Earths, different biological outcomes, but still governed by the same fundamental laws. Gravity works the same way, light travels at the same speed, and atoms behave according to the same quantum rules. But in the seventh dimension, all of those constraints disappear. Here we encounter universes with entirely different laws of physics, where everything, from forces to particles to the basic building blocks of reality, is rewritten. This is where the boundaries of imagination begin to break down. The seventh dimension is not just a variation of our universe. It is a realm in which the very rules that define existence are different. Imagine a universe where gravity is not the attractive force we know, but a repulsive force, pushing matter apart. or a universe where there are not 4 fundamental forces, but hundreds, or perhaps only 1. Perhaps electromagnetism doesn't exist, so there is no light. Or quantum mechanics behaves differently, so particles don't form the same structures we rely on. Maybe atoms cannot exist because the rules that bind electrons to nuclei do not apply. In such a universe, matter as we know it would be impossible. Stars, planets, and life might never form. Instead, reality might consist of exotic energy fields, geometric structures, or unknown forms of order beyond our comprehension. The particles themselves may be completely different. In our universe, all matter is made of quarks, electrons, and neutrinos. But in a 7D universe, there could be entirely different elementary particles that do not resemble anything in our physics textbooks. They might interact through unknown forces, form unfamiliar structures, or produce different kinds of chemistry, or no chemistry at all. Imagine a universe where the most stable atoms are 5-dimensional loops of energy, or where matter condenses into fractal networks instead of discrete particles. These possibilities arise because the 7th dimension allows the laws that govern particle interactions to be rewritten from scratch. Even the mathematics of these universes would be foreign to us. In our universe, the laws of physics rely on mathematical concepts such as differential equations, fields, symmetry groups, and quantum wave functions. In 7D universes, the mathematics itself may be completely different, built on alternate geometries, higher dimensional symmetries, or unknown algebraic structures. A universe could operate using equations our brains have no evolutionary preparation to understand. This is why the 7th dimension is often considered the limit of what the human mind can conceptualize. Here, even the logic of reality is flexible, not fixed. One powerful way to visualize the 7th dimension is to think of it as a library of all logically possible universes governed by laws that are internally consistent. Each universe in the 7th dimension represents a completely unique rulebook, a different set of fundamental principles. Some may resemble ours in certain ways, while others may be utterly alien. In one universe, time may run in multiple directions. In another, the speed of light might be infinite, instantly connecting all points in space. In another, geometry might not be Euclidean. Triangles may not exist, straight lines may bend, and distances may behave unpredictably. This raises a profound realization. Our universe is only one tiny fragment of a much larger landscape of possibilities. Just as a single page is part of a book, and a single book is part of a library, our entire cosmos, everything we see in the night sky, may be just one page in the incomprehensibly vast structure of the 7th dimension. The 6th dimension shows universes branching from identical laws, but the 7th dimension shows universes with completely new laws, creating entirely separate realities independent from ours. The 7th dimension also challenges us to rethink what existence even means. In a 7D universe, familiar concepts like space, time, matter, and energy might not exist, or they might be replaced by entirely new concepts beyond our vocabulary. To a being that exists natively in such a universe, our world might seem extremely limited or primitive, just as the flatlanders of 2D would find our 3D world impossible to comprehend. If beings could perceive the 7th dimension directly, they might see all universes, ours included, as just part of a larger structure, like nodes in a cosmic neural network. This dimension forces us to confront the possibility that what we call laws of nature are not universal truths, but simply the rules that happen to govern our universe. Gravity, quantum mechanics, electromagnetism, these are local rules, not cosmic absolutes. In the 7th dimension, those rules can vary endlessly,
producing universes that operate under new principles. So when we reach the seventh dimension, the boundaries truly break. We leave behind everything familiar, even the assumptions that shape our physical reality. The seventh dimension stretches imagination to its absolute limit because it asks us to consider not just alternate histories or alternate universes, but alternate realities governed by fundamentally different principles. It opens the door to infinite creativity, infinite possibility, and infinite forms of existence that lie far beyond what our senses can perceive or our equations can predict.
If the seventh dimension contains universes with completely different laws of physics, different forces, particles, and governing principles, then the eighth dimension goes further still. It is not simply a collection of universes with alternate laws. It is the set of all possible universes, covering every logically conceivable variation of reality. In the eighth dimension, nothing is fixed. Not the rules, not the constants, not the shapes of space, and not even the mathematical structures that define existence. The eighth dimension is the ultimate catalog, a gigantic library of blueprints for every universe that could ever exist. To understand how vast this is, let's break down what it means for a universe to differ in its laws, constants, structures, and geometries. Different laws of nature. In the seventh dimension, we explored universes where the laws of physics, the rules that govern all interactions, may differ from ours. But in the eighth dimension, we go beyond individual sets of laws. Instead, we consider all possible laws, including those that are entirely unfamiliar or even unimaginable to us. A law of physics is essentially a rule that describes how things behave. Examples include Newton's laws, Einstein's relativity, the laws of thermodynamics, Maxwell's equations, quantum mechanics. But these are only our laws. In the eighth dimension, there exists the full spectrum of alternate rule sets. Laws where time behaves differently, where motion has different consequences, where causality is rearranged, or where the universe might not evolve linearly at all. In some 8D universes, time might loop. Forces might merge or split in exotic ways. The idea of matter may not exist. Entirely new foundational principles may govern existence. The eighth dimension holds every law that could logically define a universe, not just variations of known physics. Different constants of nature. Our universe is governed by specific numerical values, constants that never change. Speed of light, c. Gravitational constant, g. Planck's constant, h. Charge of the electron. Strengths of the fundamental forces. Even tiny changes to these constants would completely transform the universe. If gravity were slightly stronger, stars would collapse too quickly. If the electromagnetic force were weaker, atoms would fall apart. If the speed of light were different, the structure of space-time would change. In the eighth dimension, we consider all possible combinations of constants, not just the ones that allow life or stable matter. There could be universes where atoms are gigantic, filling miles of space. Nuclear fusion never happens, so stars cannot form. Time moves faster or slower, depending on the constant values. Chemistry behaves in astonishingly different ways. Galaxies never take shape because physical forces cannot bind them. The eighth dimension is the space of every possible slider setting for the universe's fundamental constants, producing an infinity of different realities. Different structures of reality. Structure refers to the overall organization of the universe, how matter, energy, space, and fields are arranged or interact. In our universe, reality is structured by quantum fields, particles, energy distributions, forces, and space and time. But these structures are not universal. In the 8D landscape,
There could be realities structured by continuous energy waves with no particles, pure mathematical relationships instead of physical fields, fractal arrangements of matter, self-generating geometric patterns, multi-layered energy membranes instead of space. Some universes may have no distinguishable parts at all, just a uniform field. Others may be chaotic, infinitely complex, or made of repeating loops. The eighth dimension includes all possible structural frameworks, not just the stable or familiar ones. Different geometries. Geometry is the shape and curvature of space. Our universe uses a specific form of geometry, primarily 3D space with curvature described by general relativity. But in the eighth dimension, universes can have completely different geometrical foundations. Examples of alternate geometries include spaces with more or fewer dimensions, geometries where triangles do not obey familiar rules, spaces where straight lines do not exist, curved spaces where distances behave strangely, fractal or discrete geometries, universes that cycle through different shapes. In some 8D realities, the concept of distance might not exist at all, or might be defined by rules we can't even conceive of. The eighth dimension as a cosmic blueprint library. Putting all of this together, the eighth dimension becomes a meta realm where every possible universe configuration exists as a blueprint. Each blueprint is a fully defined version of reality with its own rules, constants, structures, geometries, potential histories, potential timelines. Imagine an infinite library where each book contains the complete design of an entire universe. Some books describe universes similar to ours. Others contain bizarre alien realities. And others still describe universes that are too strange for the human mind to imagine. The eighth dimension is this infinite library, a vast catalog of existence in all its possible forms. Every universe in the sixth and seventh dimension is just one page in this library. The eighth dimension contains all pages, all chapters, and all possible volumes of existence. It is the ultimate expansion of possibility. Why the eighth dimension stretches imagination to infinity? The reason the eighth dimension overwhelms human imagination is because it is the dimension of total freedom. Nothing is fixed, nothing is predetermined, nothing is excluded. It transcends physics, mathematics, geometry, logic as we know it, and the limitations of the human brain. We evolved to navigate a 3D world. The eighth dimension describes a landscape of realities so vast and diverse that our minds can grasp it only through analogy, such as the library of universes. It is not just the multiverse, it is the space of all multiverses, each with completely different rule sets.
Ninth dimension. Everything possible in every way. When we enter the ninth dimension, we reach a level of abstraction so immense and profound that the human mind can only grasp it through analogy and imagination. If the eighth dimension represents the library of all possible universes, each one defined by its own unique combination of physical laws, constants, structures, and geometries, then the ninth dimension goes even beyond that. The ninth dimension contains every possible blueprint library, every possible set of rules for creating a blueprint, every possible structure for organizing blueprints, every possible mathematical framework that allows universes to exist, every possible version of logic, structure, form, and pattern of reality. The ninth dimension is like a library of libraries, where each library contains infinite universes, each with infinite variations. Here, even the concept of universe becomes flexible. In some 9D realms, universes may have time, others may have none. Some may have causality,
Others may operate beyond cause and effect. Some may contain space, others may be purely abstract information. Some may have particles, others may be made of relationships or mathematics. The ninth dimension includes all forms of existence, even those that do not resemble physical worlds at all. All possible laws, meta-laws, and beyond. In 7D, we explored universes with different laws, but in the ninth dimension, even the idea of laws becomes relative. There are universes governed by equations, universes governed by logic, universes governed by probability, universes governed by information structures, universes governed by relationships rather than things, universes that cannot be described by mathematics as we know it, universes where the idea of a law does not meaningfully apply. The ninth dimension is not limited by our human framework of physics or mathematics. It includes frameworks we cannot mentally visualize, not because they are complex, but because they belong to categories of structure that our brains have never encountered. It is the dimension of all frameworks, all possible constants, meta-constants, and beyond. In 8D, constants like the speed of light or the strength of gravity could vary. But in 9D, even the spaces in which constants exist and the ways constants can exist are variables. Some universes may not use numbers at all. Some may have no measurable quantities. Some may have infinite types of constants. Some may have no constants, only dynamic, ever-shifting relationships. The ninth dimension includes not just universes with different constant values, but universes with different types of constants, or no constants at all. All possible geometries, metageometries, and beyond. In 8D, we saw universes with different shapes of space, curved, flat, fractal, discrete, multidimensional, etc. But the ninth dimension goes further. It includes all possible ways that geometry itself can work. There could be universes where geometry is non-existent. Space is a concept that doesn't apply. Dimensions fluctuate or change over time. Space is fractal at all scales. Space is emergent from deeper structures. Space is replaced by networks or graphs. Everything is built from pure information. In ninth dimension, even the idea of space becomes optional. All forms of reality, physical, abstract, logical, informational. The ninth dimension does not distinguish between physical and non-physical realities. It includes realms where reality is made of information, reality is made of interactions, reality is made of pure mathematical objects, reality is logic without space, reality is a simulation, reality is emergent from deeper meta-laws, reality is cyclical, branching, or non-linear. Reality is a single static object. Everything that can exist in any form under any system exists in the ninth dimension. The ninth dimension represents all possible ways reality can exist. To summarize, 1D through 4D describes simple movement through space and time. 5D describes alternate timelines. 6D describes alternate universes with the same laws. 7D describes universes with different laws. 8D describes all possible universes with all possible combinations of laws, constants, and structures. 9D describes all possible forms of existence, even those that do not resemble universes as we understand them. In the ninth dimension, the differences between one reality and another go beyond physics, beyond mathematics, and beyond logic. This dimension doesn't just contain universes, it contains every possible definition of a universe. It is the space of absolute possibility and absolute variation. And final analogy, the meta-library of everything. If the eighth dimension is a library of universes, then the ninth dimension is a meta-library. It contains every possible library, every possible way to organize libraries, every possible system of rules that could define a library, and every possible alternative to the idea of a library itself. It is the ultimate container of reality. The ninth dimension is the point where imagination reaches its maximum depth. This is the dimension of all realities, all meta-realities, and all conceivable and unconceivable forms of existence.
As we reach the 10th dimension, we step into a realm that transcends every boundary, every framework, every rule, and every concept our minds are capable of forming. In the 9th dimension, we explored the space of all possible ways reality can exist, every possible multiverse, every possible set of laws, every conceivable system of existence. But the 10th dimension goes beyond even that. The 10th dimension represents the absolute totality, the dimension that contains everything that can ever exist in every possible form across every possible set of rules, logic, structure, geometry, timeline, and meta-law. If the 9th dimension is the space of all possible reality frameworks, the 10th dimension is the ultimate container of all those frameworks, the final boundary that nothing can exceed. Nothing lies outside the 10th dimension because by definition, it includes all possible forms of existence. It is the final geometric or conceptual space where the distinction between alternate universes, alternate laws, and alternate structures dissolves. The 10th dimension is the infinite, unified set of every possible existence, including existences that are beyond universes, beyond physics, beyond systems, beyond mathematics, and even beyond logic itself. In other words, the 10th dimension is the space of absolute possibility, unconstrained by any rules whatsoever. 10D contains everything, all universes, all laws, all systems. Let's revisit the progression to understand what makes 10D so extraordinary. 5D contained every possible timeline of our universe. 6D contained every universe with the same laws of physics. 7D contained universes with different laws. 8D contained all possible universes with all combinations of laws and structures. 9D contained all possible ways for universes and reality frameworks to exist. So what is left for the 10th dimension? The 10th dimension contains everything in 1D through 9D, every possible definition of dimension, every possible form of logic, every possible type of existence, every meta-reality beyond universes, every possible structure for reality itself, even the concept of possible in all its variations. In 10D, there is no such thing as a universe. There is no such thing as a law. There is no such thing as geometry, time, space, or structure. These ideas only make sense inside specific universes, but 10D contains all universes and also realities without universes, so no single set of rules applies. The 10th dimension is pure abstraction, the concept of everything at once. Some physicists and philosophers describe it as the space of all possible existence, the mind of mathematics itself, the ultimate information structure, the container of all multiverses, the boundary of conceptual reality. Even these descriptions are metaphors. Human language is simply not designed to describe something as infinite and all-encompassing as the 10th dimension. Imagine trying to visualize a form of reality that includes all forms of reality, a place where every possible law and every possible logic simultaneously exist, a space where time doesn't flow because all possible timelines are included,
a structure that contains all possible structures. An existence so vast that the totality of all universes is just a tiny part of it. The human brain cannot imagine this. We evolved in a 3D world with linear time. Our mental models are limited to those constraints. To help visualize it, thinkers often use the analogy of a cosmic super library. The fifth dimension is one book, all possible timelines of one universe. The sixth dimension is a shelf, all universes with the same laws of physics. The seventh dimension is a room, universes with different laws. The eighth dimension is the entire library, all possible universes. The ninth dimension is every possible library building, layout, and design. The 10th dimension is everything that can possibly be a library or a building or any system of organizing reality. It is the ultimate abstraction, the set of all sets, the totality of all totalities, the all-encompassing whole. Nothing lies beyond it. The 10th dimension has been interpreted as the mind of reality. Some philosophers and theoretical physicists interpret the 10th dimension as the mathematical space where all patterns of existence originate, the blueprint of all possible universes, the infinite information field beyond physical reality, the ultimate unification of all systems. But these are symbolic descriptions, not literal ones. The 10th dimension in this framework is purely mathematical, purely conceptual, and purely absolute. The 10th dimension concludes the dimensional journey. As we reach the 10th dimension, the journey from 0D to 10D reveals a pattern. 0D, no movement. 1D, one direction. 2D, infinite planes. 3D, volumes in physical space. 4D, time-space. 5D, alternate timelines. 6D, alternate universes with the same laws. 7D, universes with different laws. 8D, all possible universes with all laws. 9D, all possible reality frameworks. 10D, absolute totality of existence. You have reached the highest level of this dimensional model. The 10th dimension is the final frontier, a limitless, boundless, all-inclusive conceptual space that contains everything that can ever be, ever was, and ever could be in every conceivable and unconceivable form. This is the ultimate dimension. Beyond this, there is no higher. You have reached the final level of possibility.
As we leave the conceptual 10-dimensional framework behind, we step into a realm grounded in real theoretical physics, string theory, and its modern extension, M-theory. These ideas come not from imagination alone, but from decades of mathematical research, attempts to unify all forces of nature, and the search for the deepest foundations of reality. According to these theories, the universe is not made of point-like particles, but of unimaginably tiny vibrating strings, filaments of pure energy, each just 10 to the minus 33rd centimeters long. These strings vibrate in different patterns, and each vibration mode corresponds to a different particle. Like the strings of a violin producing different notes, the strings of the universe produce photons, electrons, quarks, neutrinos, and even gravitons, which carry the force of gravity. But here's the astonishing part. For these strings to vibrate in physically meaningful ways, the mathematics requires extra dimensions. Not 3, not 4, not 5, but 11 dimensions. If the universe had fewer dimensions, the equations fall apart. If it had more, they become inconsistent. So, string theory tells us that the universe naturally has 11 dimensions, but most of them are hidden from our everyday perception. This idea is not arbitrary, it is required by the deep symmetries and mathematical structures that hold our physical world together. Star, why do extra dimensions exist in string theory? The need for extra dimensions comes from two key principles. 1. Vibrational stability. A tiny string needs enough room to vibrate in every pattern that corresponds to known particles and forces. In only 3 spatial dimensions, the string's vibrations collapse or become inconsistent. 2. Mathematical consistency. The quantum equations describing string motion require additional dimensions to cancel out internal inconsistencies like anomalies and infinities. The minimum number that works out cleanly is 10 dimensions, and when extended to include membranes, brains, the theory expands to 11 dimensions. This final unified theory is known as M-theory, where M is said to stand for membrane, mother theory, mystery, or magic. Physicists joke that the real meaning is deliberately ambiguous. Star, the dimensions of string/M theory explained. Let's break down how the 11 dimensions are structured in M theory. Dimensions 1 through 3 are spatial reality. These are the familiar dimensions we move through daily: length, width, height. They form the visible 3D space of our everyday reality. Dimension 4, time. Time is treated as an additional dimension that together with space forms spacetime. This is the stage on which all events occur. Dimensions 5 through 10, the hidden, tiny spatial dimensions. These are extraordinarily small, curled-up dimensions that exist at every point in space. They are compactified into shapes called Calabi-Yau manifolds, or even more complex geometric structures. These tiny, curled dimensions determine why the electron has the mass it has, why quarks have their charges, why forces have their strengths, how particles interact, why the universe formed the way it did. In other words, the geometry of these extra dimensions shapes the entire particle zoo of the Standard Model. Imagine each point in space not as a simple dot, but a microscopic folded shape with multiple directions. Strings wrap around or vibrate inside these shapes, and their vibrational patterns determine what particles exist. Dimension 11, the membrane dimension, the bulk. The 11th dimension is where brains exist. Massive multi-dimensional objects ranging from 1D strings to 2D membranes to full 3D brain worlds like our own. In M theory, our entire universe may be a 3D brain floating in 11D bulk. Gravity is weak because it leaks into the 11th dimension. Parallel universes could be neighboring brains separated by tiny gaps in the bulk. If 2 brains collide, they could trigger a new Big Bang, a cosmic rebirth. This model provides a possible origin for our universe and explains many mysteries, including why gravity behaves differently from other forces. What do the hidden dimensions look like? The extra dimensions are not extended like our large spatial dimensions. Instead, they are compactified, meaning they are curled up into unimaginably tiny shapes, trillions of times smaller than atoms. These forms are known as Calabi-Yau spaces, and their detailed shape determines all the physical constants of our universe. Even a tiny change in the shape of a hidden dimension could produce a completely different universe, different forces, particles, chemistry, even different types of life, or no life at all. Brains and the brain world idea. In 11-dimensional M theory, everything is made not just of strings, but also of higher dimensional analogs called brains. A 1D brain is a string, a 2D brain is a membrane, a 3D brain is a brain world like our own. Higher dimensional brains, 4D, 5D, etc., could also exist. We might be living on one such 3D brain where particles like photons, electrons, and quarks are stuck to our brain, But gravity can move into the higher dimensional bulk, making it appear weaker than the other forces. Other branes might exist parallel to our own. This leads to the thrilling idea of parallel universes, separated not by distance, but by higher dimensions. Why do 11 dimensions solve major physics problems? String theory/M theory provides elegant solutions to many unresolved mysteries. 1. Unification of all forces. String theory unifies gravity, electromagnetism, strong nuclear force, and weak nuclear force. Each force arises from different vibrational modes of strings. 2. Eliminates infinities. Point particles create infinities in quantum equations. Strings which have length smooth out these infinities. 3. Predicts gravity naturally. String theory automatically includes the graviton, the particle of gravity. 4. Describes black hole entropy. It explains why black holes have temperature, entropy, and information structure. 5. Suggests a multi-dimensional cosmos. Brane collisions can generate big bangs. Our universe may be one bubble in an 11D multiverse foam. The 11D universe, a hidden symphony. When viewed through M theory, the universe becomes a vast 11-dimensional symphony, where strings vibrate like musical notes, branes ripple like cosmic membranes, and hidden dimensions shape every property of matter. Particles are not tiny balls, they are vibrational patterns. Space is not empty, it is folded, twisted, multi-layered. Our universe is not isolated, it is one membrane among many. String theory paints the picture of the cosmos that is incredibly rich, strange, and beautiful. The final picture. String theory's 11 dimensions are the deepest attempt physics has ever made to understand the fundamental architecture of reality. In this picture, 4 dimensions shape spacetime, 6 hidden dimensions shape particle physics, 1 ultimate dimension hosts the entire brain world multiverse. Altogether, they form a complete and self-consistent mathematical structure that may one day explain everything from quantum particles to cosmic evolution.
As we move from the vast cosmic dimensions of string theory into the microscopic realm of quantum physics, we encounter a completely different meaning of the word dimension, one that defies our intuitive understanding. In everyday life, dimensions describe geometry, length, width, height, and maybe time. These are spatial dimensions we can visualize, move through, and interact with physically. But at the quantum level, the word dimension takes on a new and profound meaning. It describes the information needed to fully describe a quantum state. These quantum dimensions do not exist in space. They exist in mathematical space, called a Hilbert space. This is where quantum physics shows us that reality is not simply about where things are, it's about all the possible states they can exist in. Quantum states and probability clouds. In classical physics, a particle like an electron has a definite location. You could, in principle, zoom in and point to it. There it is. But in quantum physics, an electron does not have a single fixed position. Instead, it exists in a probability cloud, a fuzzy region where the electron might be found if you attempt to measure it. Before measurement, the electron is not somewhere in the classical sense. It exists in a superposition, meaning it simultaneously occupies all the possible positions allowed by its wave function. This probability cloud is not a literal physical cloud. It is a mathematical description of all possible states the electron can occupy. The shape of the cloud, the wave function, determines where the electron is likely to be, how it moves,
how it interacts, how it behaves in an atom. Even the iconic orbitals taught in chemistry, the S, P, D, and F shells, are not physical orbits like planets. They are probability shapes arising from the mathematics of the quantum state. Hilbert space is the true arena of quantum reality. To describe these probability states, quantum mechanics uses a space called Hilbert space. This is not a physical space. You cannot walk into it, draw it, or visualize it like a room or a grid. A Hilbert space is an abstract, multi-dimensional mathematical arena where each dimension corresponds to an independent parameter describing the quantum system. In simpler terms, spatial dimensions describe where something is. Quantum dimensions describe the state something is in. For example, to fully describe an electron orbiting a nucleus, you might need multiple quantum numbers like n, l, m, and spin. Each of these adds a new dimension in Hilbert space. The more complex the system, the higher the dimension of its Hilbert space. A single electron might require a handful of dimensions. A molecule with hundreds of electrons may require a Hilbert space with thousands or millions of dimensions. In fact, quantum systems grow in complexity so quickly that the state of 300 quantum particles requires more dimensions than there are atoms in the observable universe. This exploding number of dimensions shows why quantum physics cannot be solved using ordinary 3D thinking. Quantum dimensions are information dimensions. The key insight is this: quantum dimensions are not spatial, they are informational. They tell us what possible states a system can be in, how those states combine, how they transform, how they evolve over time. These dimensions exist in mathematical space, not physical space. The electron is not traveling through hundreds of dimensions. Rather, its wave function, its state, is described using hundreds of mathematical degrees of freedom. This is why scientists often say quantum mechanics happens in Hilbert space, not in physical space. Quantum dimensions describe what the universe could be doing, not just where things are located. Why quantum dimensions matter? Understanding quantum dimensions leads to profound insights. 1, they explain quantum superposition. A system can be in multiple states at once because Hilbert space allows it. 2, they explain entanglement. Two particles share a combined state in a higher dimensional Hilbert space, even if they are far apart in 3D space. 3, they explain why quantum computers are powerful. Quantum bits can occupy huge Hilbert spaces, allowing them to process information in parallel. 4, they explain chemistry and bonding. Electron orbitals, shapes like spheres, dumbbells, and cloverleaves, are the geometries of probability clouds in Hilbert space. 5, they explain why classical intuition fails. We evolved to understand 3D physics, not the high-dimensional structure of quantum states. Examples of quantum dimensions in action. An electron in an atom. The electron state is described by multiple quantum numbers, each adding a dimension to the Hilbert space. A quantum particle in superposition. When a particle exists in many possible positions, its wave function stretches across a high-dimensional state space. 2 entangled photons. Their joint state lives in a combined Hilbert space that is more complex than either photon's individual space. A molecule with many atoms, the Hilbert space of the molecule contains so many dimensions that no computer in the world can fully simulate it. Hilbert space versus physical space. To summarize, spatial dimensions tell us where things might be. Spacetime tells us how they evolve in time. Quantum space tells us every possible configuration of every particle. Hilbert space is not a place, it is a mathematical dimension of possibilities. This is why physicists sometimes say the real universe is not 3D, it is an evolving wave function in high-dimensional Hilbert space. This doesn't mean physical space isn't real. It means that the deepest layer of reality is information, not matter. Final insight. Quantum dimensions reveal a hidden layer of reality. In quantum physics, dimensions are no longer about geometry, but possibility. They describe the full range of states a particle or system can occupy, the rules that govern transitions between states, and the structure of quantum information that underlies physical reality. The quantum world is not a tiny version of our world. It is a vast, high-dimensional landscape of states, and our 3D experience is just one thin slice of that deeper structure. Quantum dimensions reveal that the universe is far richer and more complex than space and time alone.
When we talk about dimensions, we usually imagine neat, whole numbers, 1D lines, 2D surfaces, 3D volumes. But nature rarely behaves so cleanly. Much of the natural world sits in a strange, beautiful middle ground between dimensions, a realm where shapes do not fit neatly into 1D or 2D or 3D, but instead occupy fractional dimensions. These are known as fractal dimensions, and they reveal that nature does not always follow the tidy geometry of textbooks. Instead, it builds complexity through patterns that repeat, expand, twist, and fold in ways that break the rules of standard dimensions. A perfect example is a coastline. At first glance, a coastline looks like a long, winding curve, a one-dimensional line outlining the border of land and sea. But when you zoom in, the line becomes rough, jagged, and endlessly detailed. The closer you look, the more new shapes you discover. Tiny bays, miniature peninsulas, hidden coves, intricate patterns carved by waves and erosion. If you zoom further, the complexity continues. The coastline never becomes smooth or simple. This means it is not truly 1D because it has too much detail, but not truly 2D either because it doesn't fill a surface. Instead, it lies somewhere between 1 and 2, possessing a fractal dimension like 1.33 or 1.5, depending on the coastline. This idea that something can be in between dimensions was revolutionary in mathematics. It means that some structures have more complexity than a line, but less than a surface, and their dimensionality is a measure of how intricate they are. The more jagged, irregular, and infinitely detailed the shape, the closer its fractal dimension approaches 2. This concept didn't only transform geometry, it transformed our understanding of nature, because the natural world is filled with these in-between patterns. One of the most striking applications of fractal dimensions appears in mountains. At a distance, mountains look like 3D structures rising from the earth. But when you examine their surfaces, peaks, ridges, cracks, valleys, you discover an astonishing level of repeated detail. A mountain is not perfectly smooth like a pyramid. It is covered with layers of jagged complexity that repeat at different scales. A small rock formation often resembles the same shape as the larger mountain. The fractal dimension of mountain surfaces lies between 2 and 3, indicating that the structure is more complex than a flat surface, but does not fill space like a solid volume. Clouds, too, are fractal. Their fluffy shapes seem random, but zooming in reveals that smaller cloud clusters resemble the shape of larger ones. This self-similarity continues across many scales, giving clouds a fractal dimension between a surface and a volume. Their boundaries are so complex that they defy classical geometry.
Clouds are not simple blobs. They are fractal expressions of moisture, turbulence, and atmospheric motion. Speaking of turbulence, turbulent flows, like water rushing in a river or air swirling in a storm, are among the most fractal systems in existence. Turbulent motion does not follow smooth curves. It forms swirling vortices within vortices, each one containing smaller whirlpools within even smaller ones. This cascade of motion creates patterns that repeat at many levels of scale, giving turbulence a fractal dimension that helps engineers understand fluid behavior, weather forecasting, aerodynamics, and even astrophysical jets. Fractals also appear inside the human body. Blood vessels, for example, branch in a fractal pattern. A large artery splits into smaller arteries, which split into arterioles and then into capillaries. The branching structure repeats again and again, creating an incredibly efficient system for delivering oxygen to every cell. If the circulatory system were a simple 1D tree, it couldn't reach every cell. If it were 2D, it would waste space. If it were 3D, it would require far more material. Instead, the body uses fractal geometry to maximize coverage while minimizing energy and biological cost. The fractal dimension of blood vessels typically lies between 2 and 3, capturing this efficient balance between a surface and a volume. Even networks, like neural networks in the brain, branching roots of trees, the structure of lightning, or the pattern of rivers, share this fractal behavior. They grow, branch, connect, and self-organize in ways that are neither fully 1D, nor fully 2D, nor fully 3D. Networks optimize pathways, conserve energy, and distribute resources through patterns that repeat across scales. In the digital world, the internet itself has a fractal network structure, clusters of nodes arranged in self-similar hierarchies. Fractal dimensions show us that nature is not made of simple, perfect shapes like squares, circles, and cubes. Instead, it is made of rough, irregular, infinitely complex forms. The natural world evolves through processes, erosion, growth, turbulence, branching that create structures too detailed for classical geometry. Fractal geometry and fractional dimensions allow us to measure, describe, and understand these extraordinary patterns mathematically. The most profound insight is that nature loves fractional dimensions. Fractal dimensions appear in mountain ranges, coastlines, snowflakes, galaxies, crystals, biological systems, ecosystems, weather systems, neural networks, seismic faults, magnetic fields. They appear in chaos theory, in biology, in astrophysics, and even in financial markets. Fractals bridge order and randomness. They sit at the boundary where complexity emerges. In the end, fractal dimensions reveal that the universe is not built from simple geometric shapes. It is built from patterns that repeat, structures that grow, and processes that evolve. They show that dimensionality itself is not fixed, but fluid, stretching and bending with the complexity of nature. Fractals are the fingerprints of natural growth and natural chaos, proof that the universe expresses itself through elegant structures hidden in the space between dimensions.
As strange as it sounds, many modern physicists now believe that space itself may not be fundamental. Our deepest assumptions that space is a physical stage and dimensions are built-in features of the universe may be wrong. Instead, space may be something far more subtle and surprising, a collective illusion emerging from the interactions of microscopic elements that themselves have no spatial properties. In this view, dimensions are not basic ingredients of reality. They are emergent, like temperature or pressure, properties that arise only when enough microscopic components interact. Temperature doesn't exist for a single particle. It emerges from billions of molecules bouncing around. Similarly, space-time may emerge from billions of bits of quantum information interacting in specific patterns. This revolutionary idea reshapes our understanding of the universe. Instead of space being a fundamental arena, it becomes a derived phenomenon, a byproduct of something deeper, something more abstract. The key insight: space is not built from atoms, it's built from information. To understand emergent dimensions, imagine taking space and breaking it down as far as possible, not into atoms, not into quarks, not into strings, but into information. The idea is that the fabric of space-time is woven from the structure of quantum entanglement, the mysterious quantum connection between particles. Quantum entanglement links particles together in such a way that the state of one instantly affects the state of another, no matter how far apart they are. This network of entangled relationships forms patterns, rich, complex webs of connectivity. Modern physics suggests something astonishing. The geometry of space emerges from the pattern of entanglement itself. Distances arise from how strongly quantum states are connected. Dimension emerges from how information clusters and interacts. In this view, the universe is not a place filled with information. The universe is information, and place emerges from it. Quantum entanglement networks, the invisible skeleton of reality. Imagine a massive network of quantum bits, qubits, connected by entanglement. Each qubit represents a tiny piece of quantum information. Where the entanglement is dense, space feels close together. Where entanglement is weak, space feels stretched out. Thus, distance is not something physical. It is a measure of how entangled two regions are. Geometry is not something fixed. It is determined by patterns of information. Even dimensionality emerges from how the network is arranged. In this view, the 3D space we experience is a kind of illusion emerging from an underlying web of quantum connectivity. If the entanglement pattern were different, the dimensionality of space would change. Imagine a universe with 2D emergent space, 4D emergent space, fractal-like dimensionality depending on entanglement strength, regions where dimensionality changes over time. This leads to a profound realization. Space-time is a flexible byproduct of information, not a fundamental container. Information grids. The universe as a quantum computer. Another interpretation proposes that space-time emerges from an underlying information grid, similar to how pixels create an image on a screen. But these are not ordinary pixels. They are quantum informational units whose relationships define spatial structure. In this model, space is like a very high-resolution digital screen. Particles are like bits of data. Forces are like processing rules. Time is the updating of this quantum computation. But unlike a computer screen, the pixels, information units, are not arranged on a pre-existing grid. Instead, the grid itself emerges from how the information is connected. Thus, the grid creates dimension. The grid creates geometry. The grid creates space-time itself. This is the foundation of many theories in quantum gravity, where the universe is treated as an evolving information system. Holographic surfaces. The universe as a projection. The most stunning idea in emergent space-time is the holographic principle, which suggests that everything inside a region of space, everything we see as 3D, can be fully described by information encoded on a 2D surface surrounding it. In simpler terms, our 3D world might be a projection of information stored on a 2D boundary. This is not metaphorical. It arises from serious physics. 1. Black hole entropy. Black holes store information proportional not to their volume, but to their surface area. This means a 3D volume of space holds only as much information as is stored on its 2D boundary. 2. ADS/CFT duality. In certain mathematical universes, a complete 3D spacetime, including gravity, matter, and forces, can be mapped perfectly to a 2D quantum field theory with no gravity. This suggests the 3D world emerges from the 2D world.
3. Reconstruction of space from entanglement. Physicists found that if you manipulate entanglement patterns on a 2D boundary, you can reconstruct the shape of the 3D bulk. It's like drawing on a sheet of paper and having a 3D world inflate from the drawing. Thus, space is not fundamental, it's emergent. Space-time curves, expands, and evolves because the underlying layer of information changes. The holographic principle states that the universe works like a cosmic hologram. The deep laws of physics operate on a lower dimensional surface. The higher dimensional world is a projection of underlying information. Space emerges the way temperature emerges. Temperature is not a fundamental property. A single atom has no temperature. Temperature only makes sense when trillions of atoms interact. Likewise, a single quantum bit has no space around it. But when quadrillions of quantum interactions are woven together, a geometric space appears, like a collective property. Thus, space is emergent. Dimensions are emergent. Space-time curvature is emergent. Gravity is emergent. Gravity is no longer a fundamental force. Instead, it emerges from quantum information, just as pressure emerges from molecular motion. This is the basis of emergent gravity, an idea that ties Einstein's relativity to quantum mechanics through the language of information. The big picture: reality built from information. To summarize, what we see as space is actually quantum entanglement patterns, information processing, emergent geometry, holographic projection, a macroscopic property of microscopic rules. What we see as dimensions are actually degrees of entanglement, layers of information structure, emergent patterns of quantum interactions, not fundamental coordinates. What we see as gravity is actually a thermodynamic effect of entanglement, a response of emergent spacetime to information flow. In this view, information is more fundamental than space, time, or matter. The universe is a quantum information engine, and the dimensions we experience are the shadows cast by deeper, hidden mechanisms.